this experiment, we'll look at the Aldol reaction. And it might be helpful for me to be a little bit more specific. It turns out there's more than one Aldol reaction. There are Aldol addition reactions, there are Aldol condensation reactions, and then very related to this, there are Claisen condensations, there are Dieckmann condensations. There's kind of a host of named reactions that are all kind of in this vein of, in the same kind of mechanism. And so here, to be specific, what we're looking at is an Aldol condensation reaction. So we're going to produce water as a byproduct of this reaction. And we're actually going to do an Aldol condensation twice. So here we're going to make a kind of interesting product. We're going to take acetone, so very simple. We use that as a solvent a lot of the times, just a cleaning solvent, also used in nail polish remover. And we'll take benzaldehyde, and we'll react these together. We're going to react 2 equivalents of benzaldehyde with 1 equivalent of acetone. And we're going to end up doing a condensation. We'll form the enolate on acetone. I'll demonstrate that in a moment. We're going to use sodium hydroxide and water ethanol solvent here. And we're going to produce then the condensation, the alkenes, basically enones. So an enone, they've got an alkene adjacent to a ketone, but then it's actually a dienone, I suppose you might say here. And one of the things we'll be looking at is we want to analyze our alkene protons again in the NMR spectrum. Similar to how we did in the Wittig reaction, we can use the coupling constants, or J values, to calculate whether this comes out as the cis or the trans. I've drawn this as the trans, and I think we'll see that this ends up being just one isomer here. So we'll look at that. We'll also do a little bit of an analysis comparing the IR spectra, and of course we'll do the normal melting point analysis. So how does this reaction actually work? Well, here I've got my ketone. So I have an aldehyde here that's non-enolizable. It has no alpha protons because it's directly attached to a phenyl ring. But the acetone it is enolizable. And so the first step of this reaction is that OH minus comes and removes one of these hydrogens here to produce the acetone enolate. So just draw this here. Acetone enolate looks like this. At this point, we will have then the enolate will come and react with 1 equivalent of benzaldehyde. So this will come kick down, these will kick over there. And now I will have essentially, I'll have my acetone. And then I'll have my attachment here to the carbon that used to have the carbonyl. Now it's just up top there as an alkoxide. We've got water around, however, and alkoxides are stronger bases than water, so this is going to then pick up a proton from water, maybe the water we just generated. And so this will get protonated, and I'll have the alcohol here. And then because this is right next to an aromatic ring, and the alkene that we form if we eliminate the hydroxide is conjugated not just with the ketone but with the aromatic ring as well, that makes it very stable. And so we don't have to heat this reaction to get the condensation to go. Instead, with these really stabilized alkenes, because it has conjugation with the aromatic ring, those will simply eliminate at room temperature. So that process for elimination, we want to draw it in one step because we just want to get it done. But in reality, most of the time this does not occur in one step. It's a 2-step process. So here I've got more OH minus, comes and deprotonates, reforms the enolate here. This will then give me essentially O minus, the enolate there, and then OH. And then this kicks down, this kicks over, and kicks off hydroxide to get us to initially just a single product, just the single enone here. And so there we've got then benzyl acetone, or benzyl acetone. Now at this point, the whole reaction essentially repeats itself. Now, when I enolize, I'm not going to enolize at this position anymore because that's now sp2 hybridized. Instead, I'm going to take from the end carbon here and make the enolate, actually the kinetic enolate, on the terminal position. And then this will react with the other equivalent of benzaldehyde, go through all of those same steps to produce our dibenzyl acetone. So that's a little bit of an introduction. We'll be looking at NMR analysis to just tell us purity and also to give us some information about the stereochemistry in terms of cis or trans for my product. We'll be looking at IR analysis, just making some comparisons between starting material and product, melting point analysis to confirm whether we've made our product and its purity. So let's get our stuff together and head up to lab, and we'll get this reaction started. So here we are ready to set up the Aldol reaction in lab. Now, it's a fairly simple reaction to set up, but I need to be really careful to get good reaction stoichiometry. If I've got too much benzaldehyde, I'm going to end up with kind of an intractable product that's going to be kind of difficult to work up. If I end up with too much acetone, then I'm going to end up favoring just forming kind of the mono aldol product, benzyl acetone here. And so I really want to make sure I've got exact stoichiometry. So we're going to do this on a little bit larger scale than the pre-lab reading. I'm going to do this scaled up about 5 times. We're going to do it in a round bottom flask here with a stir bar rather than a conical vial. And what we'll do is we'll measure out 400 microliters of benzaldehyde first. And then we'll add to that, we'll add 144 microliters of the acetone, so the other starting material. And then to kick the reaction off, I have to add a base. Now, this is actually maybe the trickiest part of this reaction because I have to make up that sort of ethanolic sodium hydroxide base. So how I do that is I actually start with sodium hydroxide pellets here. And then I need to weigh out 400 milligrams. This is going to be fairly rough since this is kind of the base and catalyst. I'm going to try to get it as close as I can, but I'm not going to obsess over it. And one of the reasons I'm not going to obsess over it is that these pellets are fairly hygroscopic. So once I set this out open to air, it's going to start sucking moisture from the air. And if I were to just take a pellet and just set it on the countertop and forget about it, in a little while, that would have sucked up enough moisture from the air to actually dissolve itself into a little puddle, which would look just like water until I put my hand in it and then realized it's very concentrated and it burned my hand badly. So it's very important whenever you're working with solid bases like sodium hydroxide or potassium hydroxide, caustic bases, you should be very careful, and you also make sure that you thoroughly clean up any remaining solid. Now, I may not be able to get exactly 400 milligrams with the sodium hydroxide in the pellet form. My guess is that that's going to be too much. And so what I've brought along here is I've brought along a mortar and pestle that I can use to actually help crush 1 or 2 of those pellets and then weigh out the additional mass that I need. Now, once I crush it, I've increased the surface area so it kind of absorbs moisture from the air even more rapidly. And it's kind of a little bit of the tricky thing to weigh out because it begins to get kind of sticky relatively quickly. So we'll just have to be a bit careful with that. But essentially I need 400 milligrams of the sodium hydroxide. I'll add 4 milliliters of distilled water and then 3 milliliters of ethanol, which I've got right here. Got some ethanol. And then that solution there, it's approximately 7 milliliters of a sodium hydroxide solution in ethanol water mixture. I'll take 5 milliliters of that and then add it to my mixture of benzaldehyde and acetone. Then we'll let the reaction stir for 30 minutes. It should form a precipitate relatively rapidly. We'll let that stir for 30 minutes to ensure a complete reaction, and then we'll collect that product by filtration. So let's get started with, first of all, making up my base solution. The sodium hydroxide, this is a new bottle. It has a seal here to prevent moisture from getting in. So tear that off. And now you can kind of see those pellets there. So we're not going to want to leave this open to the moisture for very long, or to the atmosphere for very long. Let's get right to weighing this out. It's going to take a single pellet at first. Okay, so a single pellet weighs 175 milligrams, approximately. There's 380 milligrams right there. Okay, it's going to be very difficult for me to find a pellet that's anywhere near small enough to get me the additional 20 milligrams that I need. But what I might be able to do is swap out one of these pellets for a larger one. There we go. You can already see the pellets start to glisten as they pick up moisture from the air, so very important to quickly seal this off. This is good enough, 402 milligrams, that's great. Let's go ahead with that. So if you look carefully here, you probably can't see it on the camera, but they're already starting to glisten and actually stick to the whey paper. So when I go to pour these off, notice that one's kind of stuck on there. That's just from moisture. So we'll push that off there. There we go. Now I can add my water and ethanol. Here we have our 4 milliliters of water. Add that in. Now, it may take a little bit, but we're going to want to swirl this and try to get those solid pellets dissolved. Now we can see that all of that solidness is dissolved, so we're now ready to measure out and add the ethanol. Add the ethanol into our aqueous sodium hydroxide solution. And then our base 6 solution is now prepared. We're now all set to add the reagents, so I'll start with my benzaldehyde, add 400 microliters of this using a micropipette. Our benzaldehyde here, add 400 microliters of this. As mentioned in the pre-lab reading, it's a good idea to check the quality or purity of the benzaldehyde ahead of time, because benzaldehyde will slowly oxidize in air to benzoic acid. And benzoic acid would certainly slow this reaction down and be not beneficial at all. I did check it by IR and it looks pretty good. So we've got our benzaldehyde. At this point we can add our acetone, 144 microliters of acetone, again using a micropipette. So here's my acetone. I'll add this via micropipette. And then now finally I will add my 5 milliliters of the kind of ethanolic basic solution here that I made up just earlier. So we got this set. I'm going to actually add this using a micropipette. So I'll just take the micropipette, set it up to 1 milliliter, and then I'll just do kind of 5 milliliter portions of this. And I will set the stirring to begin while I do this. I'll go ahead and start the stirring here. Reaction is all set up now and progressing. We will now let this stir for 30 minutes and we should see a yellow precipitate form during this time. I will simply cap the reaction. Oh, there we go. There we see initially formation of that precipitate. It's all gone cloudy. We should see a lot more precipitate form over the next 30 minutes. Just to make sure nothing kind of escapes from the vial, I'm going to just cap it with a small cap here. There we go. We'll let this stir for 30 minutes. The reaction has now run for 35 minutes and it is very chunky, as you can see. There's a lot of precipitate, so we're going to stop the reaction now and collect that precipitate by filtration. So here we'll use the Buchner funnel to isolate our crude product. You see kind of a lot of solid settled in the bottom here. So I'll take a piece of the filter paper, place that on the funnel. I have the water aspirator already going. We'll wet the filter paper here. Make sure it adheres strongly. There we go. I'll kind of swirl everything up, make sure it's all suspended. Dump that onto the filter. See a lot of yellow material there. Very kind of precipitate-like, not very shiny. I'll remove that stir bar and rinse the material several times with distilled water to make sure I get rid of all of the sodium hydroxide that is left. I just really want that, that to be gone because otherwise it will make the recrystallization difficult later. Rinse a couple more times with the distilled water. Really try to make sure I get all of that sodium hydroxide removed. Make sure the solution is not basic in any way. It's truly neutral. And then I'll just directly rinse on the filter a couple times. Alright, at this point I should be good to let the system pull air through the solid for a while to dry it. And then I'll collect my crude product and get a crude product mass and set some aside for melting point IR and NMR. And then I'll take the remaining material and recrystallize it for purification. We'll now set a small amount of this product aside to do crude, melting point, NMR, and IR analysis. And then we'll reweigh to get the final kind of crude mass before doing recrystallization. So here we are all set to recrystallize the crude dibenzyl acetone. I've got some 95% ethanol boiling here on the hot plate. You can see that boiling there. So we got that good and hot. We can start to add that slowly into our beaker containing the crude dibenzyl acetone. So I've got that right here. So I'll begin by just adding some of that hot ethanol along the sides until I've got kind of enough here to cover the surface of the bottom. And then I can go ahead and set this on the hot plate itself. I'm going to try a single salt crystallization. If I need more, I may end up using some water. If I need to, I can do a 2-solvent recrystallization, similarly to the recrystallization for the Vidig product. But here I've added some, add just a little bit more of the hot ethanol, and then place a watch glass kind of on top of this. I'll move this off to the side, watch glass, going to put this in the center here, let this boil. You can see a lot of the material is dissolved. If there's still little bits of insoluble product, we can sort of crush those up. Here it looks like, if we zoom very carefully, it looks as though all of the solid has dissolved. We don't see any major chunks anymore there. So we are actually good to go ahead and take this off the hot plate and then let it cool and crystallize. So the solution did actually begin to form just a few crystals after scraping it. You can see those sitting there at the bottom. So I think that we just need to remove a little bit of the excess volume of the ethanol. So we'll just boil it for a little bit without the watch glass on top, and then remove it off again and let it cool. And that should be sufficient for it to then crystallize and provide us with a decent crop of crystallized material. while here. We definitely have some reduction in volume. Thankfully, the solution is still clear, so we haven't lost any material. At this point, I'm just going to remove this and let it cool again, and hopefully we'll have a better recrystallization this time. This material just seems a bit harder to recrystallize, so I'm going to scrape again with the spatula, trying to provide it a surface to crystallize on. There we go. It unfortunately isn't maybe the prettiest recrystallization of all time. Here, when I scraped, a lot of material came out as very kind of microcrystalline material, almost precipitate-like. So I'll sort of scrape just a little bit more, but most of the material here has kind of grown, but in a really microcrystalline format. So very, very small crystals, almost precipitate-like. Somewhat shiny though, and hopefully somewhat purified. See some of that material there. Crystalline, but very, very small crystals. There across the bottom. You see where I scraped with the blaster run. So we'll let this sit for a little bit and then we'll go collect this by filtration. Very small amount of 95% ethanol. Now set to get a final mass, melting point, IR, and NMR.